Hey everyone, welcome back to Math 256. This is Scott. Let's get started. So, what we are now going to be looking at is the next elaboration on what we have been looking at, and that's what happens when we have complex eigenvalues. All right. So let's consider here as a setup just the something like the following. Setup. Uh, dx dt equals ax. So in other words, we have our usual sort of a system where A has complex eigenvalues, lambda, which equals alpha plus beta I, and the conjugate of alpha, or of lambda, I mean. So quick note here, if we have a 2 by 2 matrix and we have complex eigenvalues, those came from solving a quadratic equation. And when you solve a quadratic equation, if the solutions are complex, they will come in conjugate pairs. So if one of your solutions is alpha plus beta I, another solution will be alpha minus beta I. So these are a conjugate pair. Okay, so the question, how much of what we have already been doing can we still do, and what adaptations do we have to make? All right. Well, first off, in this case, there are no straight line solutions. And in fact, what is going to be happening is that all of our solutions are going to be in some way encountering some sort of a rotation. They're all going to swirl about the origin. So solution curves will swirl around the origin. All right, well, in order to understand exactly how the swirling will happen, it will be necessary to unpack these a little bit. But let me just cut you to the punchline on this, as far as determining what sort of swirls we will be encountering. So if lambda equals alpha plus beta I, then alpha, this is called the real part of lambda, and beta is considered the imaginary part of lambda. Now, if so, we'll just state what the grand summary is here, and then we'll see how it actually plays out as we develop it. So if alpha equals 0, the solution curves just orbit around the origin. And what that looks like is you just have something like this. Maybe it's going around clockwise, maybe it's going around counterclockwise. That's all a question that depends on some very specific things that are not really worth our attention here. And this then is called a center. Called a center. If alpha is not equal to 0, then there are two possibilities. Either it's greater than 0 or less than 0. So if alpha is greater than 0, the solution curves spiral outward from the origin. And so what that looks like is you see something like this. And then the origin is called a spiral center, or sorry, a spiral source, I should say. The origin is then called a spiral source. And then I think you can probably imagine case number 3. If alpha is not equal to 0 and is not greater than 0, then that means alpha is less than 0. And you can probably even guess what's about to happen here, the solution curves. Spiral inwards. Oops. Toward the origin. So its silhouette maybe looks a lot like this one, except the difference is that the direction of motion is different. And this is called something you might be able to predict. The origin is then called a spiral sink. Okay, now if we want to actually solve these systems rather than discuss them in vague terms like this, then we need some tools. So solving such systems. All right. Well, first off, what we absolutely have to start by doing is finding the eigenvalues. Find eigenvalues lambda, alpha plus beta I, and lambda conjugate, alpha minus beta I. Okay, now 2. Find a complex eigenvector v for lambda. And the key to this is to do a very similar operation to what we did in the real case. All right, but anyway, then 3, use Euler's formula. So E the alpha plus beta I t is equal to e to the alpha t e to the uh, e to the beta I t, which then is equal to e to the alpha t times, and now here what we have is e to a power of an imaginary number. So what the Euler's formula here is when we have anything of the form e to the ix, that's equal to cosine x plus I sine x. If you've never seen anything like this before, the origin of it can come from a couple different considerations. One consideration would be if you know the complex, or sorry, if you know the infinite series expansions of e and cosine and sine, then just try expanding out this one and see what happens. Another consideration would be if you were to think about the derivatives. Think about the derivatives in sequence of these. They would form a little cycle of 4 derivatives, and they would all correspond with each other. And it's not a coincidence that they would do so. But what this then would unpack into is cosine beta t plus I sine beta t. So use this to multiply out e to the lambda t v, then collect the real and imaginary parts of the result. And of course, what real means is no mention of I, and what imaginary means is the term that has the coefficient of I. The terms without and with I, respectively. All right, then call these x r e and x I m for x real and x imaginary. Then the solution will be x equals c1 x r e of t plus c2 x I m of t. And then if there are any initial conditions, so that's all step 3. Then step 4, if there are any initial conditions, find the C1 and C2. If initial conditions are given, find C1 and C2. All right. Let's give this a try. So as an example, let's just say solve. And so for the first one, we're going to be dealing with a differential equation dx dt equals ax, where a equals 5, -4, 5, -3, and x of 0, so in other words, the initial conditions, equals 2, 1. So let's just see if we can figure out how this whole process is supposed to work. Up till now, it's been very theoretical. Now is where the rubber meets the road, and let's see what we can do. Okay, so we've got to start by finding the eigenvalues. So let's just go ahead and see where that takes us. So a minus lambda I. We do not change anything about our general approach here. It's just that when we solve these, we're going to end up with some perhaps imaginary results. So 5 minus lambda, -4, 5, -3 minus lambda. Nothing different here. In fact, still nothing different. We just take the determinant. And what's that give us? 5 minus lambda, -3 minus lambda. So -4 times 5, so in other words, plus 20. So 0 equals, and what do we have here? We have positive lambda squared. We've got, for the middle terms, we have -5 plus 3, so that's going to be -2 lambda. And then what do we have here? We have -15 plus 20 is going to be plus 5. Okay, so here is the lambda, and we can't factor this. We could do a difference of squares type thing, but let's not worry about that right now. Let's just use the quadratic formula, a, b, and c. So -b plus or minus square root of b squared minus 4ac all divided by 2a. So it's going to be positive 2 plus or minus square root of b squared is 4 minus 4ac, so minus 20 divided by 2a. So 2 plus or minus square root of -16 over 2. In other words, 2 plus or minus 4i. So if you remember, when you're taking a square root of a negative, and we are talking about now potentially complex results, then it's just whatever the square root was going to be, and then you put on an I if it was negative. And then we can distribute the 2 into both of these, and we get 1 plus or minus 2i. Okay. Now, here's how to find the eigenvector. A minus lambda I is equal to 5 minus 1. So I'll pick here lambda equals the positive. We're always going to, by default, choose the positive side here. 1 plus 2i, 5, -4, -3 minus 1 plus 2i. And then what we're going to do here is have 5 minus 1 plus 2. So that's going to be equal to 4 minus 2i minus 4, 5, 4 minus 2i. Okay, now our approach once again is not going to really differ from how we have done these things in the past. So we're just going to take this and we're going to just say 4 minus 2i, negative 4, 5, negative 4 minus 2i, xy equals 0, 0. So I have 4 minus 2i times x minus 4 times y equals 0. I will divide both sides by 2 just to clear that up a little bit. 2 minus I x minus 2y equals 0. And then I'll just move that over to there, and I'll have 2 minus I times x equals 2y. So I can just say x equals 2, y equals 2 minus I. And then that means that v is going to be just 2 and 2 minus I. Now, as a note, so this is one eigenvector. For the conjugate, we could use just the conjugate of our v. So that would be 2 and 2 plus I. Just wherever you have an imaginary term, it just goes from negative to positive or positive to negative. Okay. Anyway, that's all well and good. But now we are supposed to be expanding e to the lambda t v. So we're not supposed to really actually be worrying that much about the conjugate right now. So let's just see where this takes us. This is going to be e to the, what was our lambda again? 1 plus 2i. 1 plus 2i t times v, which is 2 minus I, which is just going to be equal to e to the t times e to the 2i t, 2 minus I, which finally now we get to break out Euler's formula, and we'll have cosine 2t plus I sine 2t, 2 minus I. And now I just distribute this expression into these two pieces. So e to the t, and I'll have 2 cosine 2t plus 2, I2 sine 2t for the top one. For the bottom one, you basically would just FOIL it all out. So 2 cosine 2t minus I cosine 2t plus I times 2 sine 2t, and then I times I is negative 1. This is going to be plus sine 2t. And this one is because negative I squared equals 1. And then I can basically separate out the imaginary and the real parts here, and I would get x real is equal to e to the t times 2 cosine 2t. And on the bottom, we'd have 2 cosine 2t plus sine 2t. And x imaginary will then represent all of the pieces of this that do have an I, so still e to the t in front. 2 sine 2t. And then negative cosine 2t plus 2 sine 2t. And we don't write the I on these. The imaginary part is actually just the part that I is the coefficient of, or in other words, the coefficient of I. And so then we would have the general solution x of t is equal to c1 e to the t 2 cosine 2t 2 cosine 2t plus sine 2t plus c2 e to the t. And there are a number of different ways you could write this. 2 sine 2t negative cosine 2t plus 2 sine 2t. And for example, another way you could write this is to distribute in the e to the t's and the c1 and c2, and then just put those all in one line. But we won't bother with that. Now, the initial condition was x of 0 equals, what was it, 2, 1. So what that means is 2 and 1 are what we get when we have c1 times, and we're plugging in t equals 0. So it's going to be 2 for the first one, 2 on the second one. Remember, cosine of 0 equals 1, sine of 0 equals 0, and e to the 0 equals 1. C2, 0, negative 1. And so, actually, just looking at this, a solution jumps out. I can see, and you can solve this by any means, but you can see that 2 equals 2c1, which implies that c1 equals 1, and then 1 equals 2c1 minus c2, and so 1 equals 2 minus c2, so add, subtract, and you get c2 also equals 1. And so then that gives us our particular solution here of x of t is equal to just 1 and 1 for our two coefficients. So it's e to the t 2 cosine 2t 2 cosine 2t plus sine 2t plus e to the t 2 sine 2t negative cosine 2t plus 2 sine 2t. And now I can actually combine these into one big expression, so I can get e to the t, and it's just going to be 2 cosine 2t plus 2 sine 2t. And down here, it looks like it's just going to be 2 cosine minus cosine, which is going to cancel out to make just cosine. So you get this. Now, what is going on in this solution? Well, if we look at it, so we kept our head down, we did our math, we did a lot of math, and it was pretty fancy math. But now that we have done the math, let's take a look at what we have wrought. So what we have here is an expression that involves cosine and sine. And if you make a parametric expression that involves cosine and sine like this, you expect it to involve some sort of a rotation. And also, if we look over here, we have an extra factor of e to the t on top of everything else that's happening. And that is what is causing it to spiral outward. We have x and y values that would be sinusoidal, except that they are also being inflated by a factor of e to the t. So this is a spiral source at the origin. And we don't know if it's going clockwise or counterclockwise. If you actually really wanted to know that, and if you wanted to know whether it was an ellipse or a circle or what have you, that would actually require some kind of fancy trigonometry. You would need to figure out how to combine these each into a single trigonometric expression in sine or cosine, and then figure out what the phase difference was between here and here, and it would just be, it'd be a thing. It could be done, but it's not really worth our while to go into that kind of detail. The most important thing for us is producing solutions on the one hand, and also characterizing the nature of the equilibrium at zero on the other, into the categories of spiral source, spiral sink, or center. Okay. Well, let's just try this again. So this was all just us executing the rather intricate plan of action as indicated on the instructions. But now let's just try it again and see what happens with another one. So let's go with, now we'll just say, I'll just cut to the a. A equals -3, 1, -2, -1. So let's just say we have something like this. So here now we can just see where this takes us. So a minus lambda I is going to be -3 minus lambda 1, 2, and -1 minus lambda. And then that means the determinant of the same is going to be -3 minus lambda times -1 minus lambda, and then minus 1 times 2, so 2. And now we'll set it equal to 0. We're going to have a lambda squared. What are we going to have for the constant? Looks like +1 plus 3 is going to be +4 lambda. And then what are we going to have for the other part? We're going to have, it looks like we're going to have +3 minus 2. It's going to be +1. Oh, sorry. This was supposed to be negative. Okay, that makes more sense. I was going to say something fishy here. Okay, so what is this now? It's going to be +3. So that's going to be plus 5. Okay, so then what's that going to lead to? It's going to be a equals 1, b equals 4, c equals 5. Or you can do this by completing the square. I welcome that. That would be a fun way of going about this. But we'll just do it the classical way with the quadratic formula. So then it's going to be -4 plus minus square root of 16 minus 4ac, so divided by 2a. It's going to be negative 4 plus or minus the square root of negative 4 over 2, which is going to be negative 4 plus or minus 2I over 2, which is then just going to be negative 2 plus or minus I. So by the way, right here I can see this is going to be a spiral sink. As soon as I have the eigenvalue, I actually know that much. So then I'll take my lambda equals negative 2 plus I. And I'll figure out a corresponding eigenvector. A minus lambda I would be equal to negative 3 minus negative 2 plus I, 1, negative 2, and negative 1 minus negative 2 plus I, which is going to be equal to negative 3 minus negative 2 is going to be negative 1 minus I, 1, negative 2. Over here we'll have 1 minus I. And so then I can just take this and apply the usual rigmarole, which is to multiply it by xy and find the combination of x and y to make it equal 0. And just by default, just to avoid anything unexpected, I'll just go with the first one here. Negative 1 minus I times x plus 1 times y equals 0. So then if I move this over to the other side, I'll have y equals 1 plus I x, and I just did that so I would have positives just because of a prejudice towards positives. So x equals 1, y equals 1 plus I, and that means that v is going to equal 1 and 1 plus I. Okay, just going through the steps here, then e lambda t v, we just can expand that out, so it's going to be e to the negative 2 plus I t 1 over, oops, not 1 divided by, but 1 on top of 1 plus I, which is going to be, so if I distribute the t here, it's going to be e to the negative 2t, e to the it, 1 plus I, e to the negative 2t, cosine t, plus I sine t, one plus I. And so then we would distribute this. Cosine t plus I sine t. And you would FOIL this all on the bottom. So it'd be cosine t plus I cosine t plus I sine t plus I squared, which is going to be minus sine t. Which then I can break up into the two pieces, the imaginary and the real parts of the solution here. So x real would be the e to the negative 2t. And now I just look at all the terms here that don't involve an I. It's going to be a cosine t up top. It's going to be a cosine t minus sine t down below. And the x imaginary. It's going to be e to the negative 2t sine t. So again, we don't write the i's here. Cosine t plus sine t. And then that means that our general solution here is going to be c1 e to the negative 2t cosine t cosine t minus sine t plus c2 e to the negative 2t sine t cosine t plus sine t. And if we had initial conditions, we would now put them in and see what we would get from this. So once again, what we need to get the C1 and C2 specified would be an initial value for C1, or sorry, for X and for Y. All right. Now this, because of its negative real part of its eigenvalue, is going to be, again, as we said, a spiral center, which means it's going to spiral inward. We don't know exactly what direction. This is just speculative, but it's a spiral center. A spiral sink. Spiral sink. So it's spiral sink. And and we won't see this very often, but if it turns out that this beginning part is e to the 0t, then it's not actually exponentially decaying in radius, and it's not exponentially growing in radius. And as a result, we end up with a center which is technically actually stable. But that's again not something we're going to see a lot of, so we're not going to worry about it. We'll see that more when we practice the technique that is called linearization. Then it'll happen sometimes, but not so often right now. All right, well, let's have a look then at what Bluffton has to say about the looks of systems such as these. All right, here we are back at our Bluffton. So once again, we are talking about systems here. Let's have a look at what the slope fields look like for the two examples that we just saw. So for example, A, the differential equation had coefficients 5 and -4 for the x and y. So 5, -4 on the top. And then on the bottom, it was 5 and -3. Okay, 3y. Okay, so now just looking at it, if we remember what the deal was supposed to be, we are supposed to be talking about about a spiral source here, and you can definitely see now why it's called that. The solution curves are all spiraling outward from the origin. Notice they're spiraling in this sort of elliptical manner with a slant to it. And if we clear all our curves here and we put in the initial conditions that we were specifically given, 2 and 1, then what we get should actually correspond to the specific solution that we found by actually solving and plugging in the initial condition and getting the answers. And in fact, if we wanted, we could verify that by actually graphing in here. The third option in is a parametric graph in T, which is what we would want to be producing here And the way we would do that is we would do e to the, we'd have to go e to the t 2, and you could arrange it in many different ways. I'm just going to do 2 cosine 2t plus, I'm going to go ahead and put parentheses here. So my e to the t is times all of this, plus 2 sine 2t, end the parentheses for the e to the t, and then comma, and you put in the next one. So it'd be again e to the t, and then times in parentheses cosine 2t plus 3 sine 2t. So if I clear all my curves and I just put this one in and I put in, so I need some negative values of t to get closer to the origin. Then that is, so that is now my solution curve as graphed, just sort of as a function. And now I submit this and look at my, look at the solution curve that, that Bluffton generates. So take this one off and we can still see the Bluffton one. Now, just as a note, if you go around changing this to something like Euler, then you can see that the solution curves start to diverge from each other, and they start to diverge from each other rather dramatically around this part here. That's just a fact. When you use Euler, it starts to fall behind when you have the abrupt changes in slope that you see right here. So we observe a function that is very, very quickly changing, and Euler's method is just too slow on the uptake to adjust in real time to the changes as necessary. And it would be even worse if the step size were bigger. But back to the Runge-Kutta, notice what a nice method that one is. You can't even see any difference between the two curves. All right, so that was the first one, the spiral source, and sure enough, it is definitely doing spiral source stuff. Now the second one, the second differential equation, or sorry, the second system that we looked at had -3 as the first coefficient, and then 1, so in other words, plus y for the first. And I guess we don't need this one anymore. And then second equation was -2, -1. So -2x minus y. Okay, so this one is supposed to be a spiral. This one's supposed to be a spiral sink now. And you'll notice, sure enough, wherever it starts, it ends up draining down at the origin like a sink. We didn't plug any specific initial conditions in on this one, but if we had, we would expect a very similar result to what we saw before. It would, if we gave it an adequate range of t, then we would see something that managed to fit what we had pretty well. Just sort of graphically, the difference between this one and the very first slope field that we did in the previous section, the one where we were talking about the two distinct real eigenvectors, and they were, but the two eigenvectors were close to each other. The difference between these two situations is these ones actually are capable of executing almost a full rotation here. We can see that it is capable of wildly swinging around, and there is no one direction that they all end up approaching the origin at. It's all a question of where their spiraling path takes them. You can approach the origin from there, from here, all sorts of different ways. And so you get really you get really a full spectrum of motion. Whereas the other ones all end up approaching the origin along one specific line. It's like there's a runway at the origin, and all the trajectories have to vector along that one specific path. So this one, though, they can approach it from pretty much any direction, and they just spiral their way in towards the origin. All right. So the basic adjustment that we had to make once again for complex eigenvalues was rather than being able to just use the eigenvectors and the eigenvalues, we had to do a little bit of creative use of some of the fancier techniques out there, including Euler's formula, which connects the sine and the cosine with the exponential function through the medium of complex numbers. And that is fundamentally why we get these sort of oscillating solution curves and circling solution curves, is because when we are talking about complex situations, the easiest way to understand them is in terms of the sine and the cosine through the bridge that is Euler's formula. But anyway, the procedure here takes a little bit of getting used to, but it is a very tried and true, relatively reliable procedure. So hopefully with a little bit of practice, you'll be able to master it. All right. Well, this concludes our discussion of complex eigenvalues for the moment. When we come back in the next episode of Math 256, we'll talk about what happens when your eigenvalues are repeated. So far we've talked about distinct eigenvalues and complex eigenvalues, but what if your eigenvalues are repeated? To find out, tune in for the next episode of Math 254. Till then, bye.